In this video, we will cover the common pretreatment and post-treatment components typically associated with a reverse osmosis system used for the production of water for hemodialysis. We will discuss the reason that each component is part of a hemodialysis system and what daily checks, tests, and record keeping is associated with each component. An example of a daily log sheet is Marcor Purification's Tech Note 141. But your facility will likely have their own specific daily water treatment log that you will need to fill out. Incoming feed water contains solutes that exceed the safe levels needed for making dialysate. Although these levels of solutes may be safe for drinking water, they are considered contaminants if above the safe levels for the production used for hemodialysis. The Association for the Advancement of Medical Instrumentation, known as AMI, has developed a list of water contaminants and the allowable levels of these contaminants in water used for the preparation of concentrate from powder, for reprocessing dialyzers, and for the preparation of final dialysate. This chart lists those contaminants and the maximum concentration in water used for hemodialysis. Approximately 94% of the fluid in the final dialysate is composed of RO water, and if the water is not treated properly, the dialyzer membrane will be the only barrier between any contaminants and exposure of these contaminants to the patient's blood. If the levels are not reduced to safe levels, a variety of patient symptoms and reactions can occur. This chart shows some examples of patient symptoms of being exposed to inadequately treated water. The possible patient symptoms can run the range from nausea to death. The symptoms and reactions will depend largely on the type of contaminant and the levels. A variety of pretreatment components are needed to pretreat the water before it enters the RO. This pretreatment is necessary for the safety and optimal performance of the RO membrane, and most importantly, for the safety of the hemodialysis patient. The backflow preventer is a check valve on the incoming feed water that prevents pretreated water and disinfectants from backing up into the municipal water supply. The backflow preventer is required by many municipalities, but is not required in all states. Testing and monitoring requirements are determined by local codes and authorities and is typically done annually by an outside vendor. The temperature blending valve mixes hot and cold incoming water to a fixed, predetermined temperature. The ideal temperature is 77 degrees Fahrenheit or 25 degrees Celsius. The blending valve will help achieve optimal performance for the reverse osmosis machine and protect other water treatment equipment, RO membranes, and dialysis equipment from excessive temperatures. A thermometer after the blending valve will indicate the incoming feed water temperature. Record the temperature gauge readings on the pretreatment log sheet. Some systems may not use blended water and will run using only a cold water source. Depending on the geography of the location, this water may be very cold in northern locations and very warm in southern locations. This lower and higher temperature will affect the product flow and water quality of the RO membranes. Whether using a blending valve or having a system without a blending valve, the temperature of the incoming water must be within the specifications of the RO membranes and all pre- and post-treatment water components. The feed water booster pump raises the incoming water pressure to a desired level for stable system operation. The pump operates in the event of low incoming water pressure in order to maintain demands within the proper range for all water treatment equipment. A bladder or pressure tank may be used in conjunction with a booster pump to hold a volume of water at a designated pressure. The tank releases water when downstream components generate demand. Record the inline pressure gauge readings. Pressures will vary, but normally should be around 50 facilities increase the pH of the water in order to minimize leaching of lead and copper from piping. Carbon tanks and the RO don't function well if the incoming pH is too high. If needed because the incoming pH is too high, a chemical feed pump can be used to adjust the pH of the feed water by dosing small amounts of chemical into the feed water. The most common chemical used is sulfuric acid. Automatic controls and monitors can get out of calibration and need to be checked, and the pH may be tested from a sample port after the chemical feed pump to assure the appropriate pH is being met. This testing may either use a pH test strip or a pH meter. Pretreatment tanks such as multimedia, softener, and carbon tanks are available in a variety of tank sizes to fit individual facilities' needs. Configuration of these tanks may vary to meet individual facility needs and conditions. Tanks come in either blue or natural color. The multimedia filters are used to filter out particulates larger than approximately 20 microns. For comparison purposes, the diameter of an average human hair is approximately 100 microns. Not all water systems will have multimedia filter tanks. Depending on the feed water source, some facilities may use multimedia cartridge filters or have no need for any multimedia filtration. Water in the multimedia filter tank is filtered through multiple layers of various sized gravel, sand, and anthracite, which is a specific variety of coal. The multimedia filter will automatically be backwashed to rinse out collected particulates, so timers need to be checked. If the filter goes into backwash during times of patient treatments, the RO will be locked out and shut down. Recording pre- and post-filter pressures may be part of your softener is designed to eliminate hard water commonly found in the incoming water supply and provide soft water in an effort to protect the RO membranes from scaling, which can lower RO production. Softeners use an ion exchange process to remove incoming water hardness, such as calcium and magnesium, in exchange for sodium ions. It includes a brine tank which holds a sodium chloride salt solution and a control system to regenerate the softener at preset intervals. To perform the daily softener checks, 1. Ensure that the timer is set at the correct time of day and the dot on the regeneration knob is aligned to the time of day arrow. Incorrect timer settings may cause the water softener to regenerate during dialysis and can result in automatic shutdown of the RO. 2. Ensure all water supply valves are open, bypass valves are closed. 3. Check the brine tank level daily to be sure the tank is at least half filled with salt, adding salt pellets if necessary. Water may become hard if the salt pellet level is low. 4. Observe and record inlet and outlet pressures and the difference in pressure. If the difference is greater than 10 psi, the softener needs to be backwashed. 5. Using the sample port directly after the water softener, test and record the water hardness at the beginning and end of each treatment day. Results should be 1 grain per gallon or less, or as specified by clinic management. Notify appropriate personnel if hardness test is greater than 1 grain per gallon. Scavenger tanks are not a common piece of pretreatment, but can be used if the feed water contains elevated levels of organic materials. Organics can form deposits and clog up the carbon media. Scavengers can come as single or dual tanks. The resin in the tanks need to be regenerated. And check that the salt level in the brine tank is at least half full. Daily timer checks and daily pressure readings, similar to those of the water softener, should be done if you have these tanks in place. The carbon tanks are used to remove chlorine, chloramines, and some organics by depth filtration, utilizing activated carbon. Carbon tanks are designed to adhere incoming chlorine and chloramines onto the surface of the carbon media from the incoming water supply in an effort to protect the RO membranes and patients from harmful levels of exposure. Two tanks are used in series: the primary, also called the worker, and the secondary, also called the polisher. These two tanks, or groups or banks of tanks, in series, should provide a total of 10 minutes of empty bed contact time, or EBCT. To perform the daily checks on the carbon tanks: 1. Ensure that the timers are set at the correct time of day and the dot on the timer knob is aligned with the time of day arrow. Incorrect timer settings may cause the carbon filter to backwash during dialysis and can result in automatic shutdown of the RO. Record the inline pre and post carbon filter pressure gauge readings. 2. Operate the carbon tanks with the RO running for a minimum of 15 minutes to flush the carbon tanks and provide fresh water for testing. 3. Test the carbon tank output water to verify absence of chlorine/chloramines and record the results on the log sheet. Using the sample port directly after the first carbon tank, test and record the total chlorine levels at the beginning of each patient shift. Results must be less than or equal to 0.1 ppm total chlorine. Notify appropriate personnel if total chlorine level is greater than 0.1 ppm. After the pretreatment, the water will enter the RO, where a portion of the water will pass through the RO membrane and become purified product water. After the product water leaves the RO, it must be distributed to the various points of use. This water has been highly purified at this point, and various post-treatment components are needed to keep the water in as pure a state as possible. The variety of post-treatment components will depend on the type of distribution system that is being used. In a direct feed distribution system, product water is pumped directly to the distribution loop from the RO. Some direct feed loops return some product water back to the RO for reprocessing. Indirect feed distribution systems use a holding tank and recirculation loop where the product water is pumped into an RO storage tank. A distribution pump distributes the water from the storage tank through the RO water loop to each point of use. The water not used by hemodialysis machines, concentrate mixers, and any other point of use is returned to the storage tank. The storage tank collects product water from the RO and the product water that is returned from the distribution loop. A typical tank will have 3 level switches: a high level switch which will tell the RO to go into standby mode when the tank is full, a low level switch which will tell the RO to turn back on and start producing purified water, and a low level switch which indicates that the tank is near empty and will activate an audible and visual alarm. This switch may be wired to turn off the distribution pump to prevent the pump from going dry and burning out the pump. The storage tank distribution pump boosts the water pressure from the tank through the distribution loop. Deionization tanks, also referred to as DI tanks, can be used as the main component to purify the water used for dialysis, or as an additional treatment process after the RO. DI is an ion exchange process using synthetic resins that remove anions and cations and replaces them with hydrogen ions and hydroxide ions, which then combine to form pure water. If the feed water has a high level of dissolved solids, the RO system may be unable to reduce the levels to meet AMI standards, and DI tanks may be used to further purify or polish the product water. DI can be used as a backup method for purifying water in the event the RO, the storage tank, and/or the distribution system malfunctions. Appropriate carbon filtration must be utilized before the DI tanks in order to remove chlorine and avoid the formation of carcinogenic nitrosamines. All DI tanks must be followed by a pyrogen or endotoxin filter. Monitoring of the DI tanks typically use a red and green light between the tanks, and the final DI output must be equipped with a continuous temperature-compensated monitoring device that will cause a visual and audible alarm and divert the water flow to the drain in the event that the water quality no longer meets the acceptable standard of 1 megohm per centimeter or higher. Water produced by the RO is very clean but is not sterile, and it may contain very low levels of bacteria. These bacteria can increase in number in the distribution system, and this number needs to be kept to a minimum. The ultraviolet purifier, typically called the UV, is designed to reduce bacteria and other microorganisms that can be found in the pure water system. The UV uses an ultraviolet lamp to destroy bacteria and other microorganisms that may be present in the water. The byproduct of the UV killing bacteria is that the outer membrane of these bacteria break apart. The byproduct of this outer membrane disintegration are referred to as endotoxins. These endotoxins can elicit a very strong immune response and cause very severe reactions in patients. Because of this negative patient response to endotoxins, the UV must be followed by a pyrogen filter, endotoxin filter, and/or ultrafilter to trap any endotoxins produced as a result of the UV light killing bacteria. The ultrafilters are designed to capture and eliminate bacteria, endotoxin, and other microorganisms that may be present in the pure water system. Ultrafilters are typically found on a storage tank and following DI tanks and UV purifiers. This membrane filtration device removes organics in the 0.002 to 1.0 micron range. Monitor the inline pre- and post pressures on the ultrafiltration device. Please refer to the product inserts and manuals for each component for additional and complete information.